So in mathematics, we are interested to know if the graph of a function has symmetry in respect with the x-axis or the y-axis or the origin, the point 0, 0. Can we find that out actually without graphing yet algebraically? And the answer is yes. So we are going to talk about the three types of symmetry in this short and to the point video. Symmetry in respect with the x-axis, in respect with the y-axis, and in respect with the origin. Let's start with symmetry about or in respect to the x-axis. Suppose I have x equals y to the second. And the reason I'm choosing this, because I know that the graph of x equals y to the second is a parabola that is opening to the right, something like this. And I want to know if this does have a symmetry in respect with the x-axis. So what I need to do to show symmetry algebraically is to replace y with negative y and simplify. If the resulting say function is the same as the original, then we have symmetry, or I should say the graph has symmetry, then the graph has symmetry in relation with x-axis. Okay. So in this case, let me go to the next page. I have x equals y squared. I have x equals y squared. So I'm going to change the y with negative y. So x equals minus y to the second power. Now, this is the same as saying x equals minus y times minus y. So x equals negative times negative is positive. Y times y is y to the second. So notice that I got the same function back, the same equation back. So therefore, yes, x equals y squared does have symmetry in relation with the x-axis. Let's do another example. Suppose we have y equals, let's say, x to the second, this time plus 2x. Does this graph, or does the graph of this equation or this function have symmetry in relation with the x-axis? Let's see. So notice that this one's actually really easy, because if I change y with negative y, this equals x squared plus 2x. And if I now multiply both sides of this equation by negative 1, I get y equals minus x squared minus 2x. And that's not the same as the original function. So therefore, there is no symmetry in relation with the x-axis. Let's do one more in relation with the x-axis. Suppose I have x equals y to the power of 4 plus y to the power of second plus, let's say, 3. Okay. And now I'm supposed to change every y with negative y. So x equals negative y to the fourth power plus negative y to the second power plus 3. So x equals negative y to the power of 4 is indeed positive y to the fourth power. And negative y to the second power is indeed positive y to the second power. And here's my plus 3. So notice that exchanging y with negative y didn't make any difference. So therefore, we do have symmetry in relation with the x-axis. So one last time, if you want to know that your function or your equation has symmetry in relation with the x-axis, you must replace y with negative y and simplify. If you get the original function back, then there is a symmetry in relation with the x-axis. If not, you simply don't have symmetry in relation with the x-axis. How about y-axis? How do I know if a function or graph of function has symmetry in relation with the y-axis? Well, in this case, we exchange x with negative x. So to see if a function has symmetry in relation or in respect to the y-axis, replace x with negative x and simplify. Example, let's say y equals x squared plus 4. So now I'm going to exchange the x with negative x to the second power plus 4. So this is the same as y equals x squared plus 4, which was my original one. And therefore, yes, we do have symmetry in relation with the y-axis. Something noteworthy is that the functions that have symmetry in relation with the y-axis are called even functions. So even functions have symmetry in relation with the y-axis. The previous examples that we did in relation with the x-axis doesn't have a name. We don't have a particular name to identify symmetry in relation with the x-axis. So, but with the y-axis, we call those even functions. Let's do one more example. How about y equals x to the fourth plus x to the second minus 10. So y equals minus x to the fourth power plus minus x to the second power minus 10. So y equals x to the power of 4 plus x to the power of 2 minus 10, which is my original function. So this one is even function. So, and it does have symmetry in relation with the y-axis. And the last case scenario we want to discuss is the symmetry in relation with the origin. And we call those odd functions. If graph of an equation or a function has symmetry in relation with the origin, then we do have an odd function. So last one, third case, with respect to the origin. That is 0.00. Okay. So in order to find out if a function has symmetry, graph of a function has symmetry in relation with the origin, we exchange both x and y with negative x and negative y. So to test, exchange y and x with minus y and minus x. If you get the same, if you get the same or the original function back, then we have symmetry in relation with the origin. The most basic example of that would be y equals x cubed. Y equals x cubed is the most basic odd function that we know. So let's show that. We said that exchange x and y with negative x and negative y. So now I have minus y equals minus x cubed. So in left-hand side, I have minus y. On the right-hand side, I have minus x times minus x times minus x, which is minus x cubed. And notice that if I multiply both sides by -1, I get y equals x cubed, which is the original function. So y equals x cubed does have symmetry in relation with the origin, and we said we call those odd. Let's do one more example. How about y equals x cubed plus x? Okay, so minus y equals minus x cubed plus minus x. And so this is minus y equals minus x cubed minus x. And notice that here what I can do is factor a negative out, and then I have x cubed plus x. And so, excuse me, divide both sides by -1 or multiply by both sides by -1, and you get the original y equals x cubed plus x back. And so therefore this one is odd. This function is odd function, and it does have symmetry in relation with the origin. So what is really concerning that most students think that, oh, this is easy. So if the power is odd, it's an odd function. And if the power is even, it's even function. Not so. Let me just show you an example. If I say f of x equals, let me just change that to y equals x cubed, okay? And let's make that x cubed, let's just make it plus a 2. So by that rationale, that if you're thinking if it's odd powers, then the function is odd. No, not so. Let's look at this one. What happens if I exchange this with -y and then negative x cubed plus 2? So I have minus y equals minus x cubed plus 2. Now, if I factor a negative from right-hand side, I will get minus y equals minus x cubed minus 2. And dividing both sides by -1 or multiplying by -1 gives you y equals x cubed minus 2. And that is not the same as the original one. And one last thing to say is, what if you have a combination of, let's say, y equals x to the second plus x? One of them has even power, the other one has odd power. So you can't just, generalize that if they have odd, even powers, then the function is even or if they have odd powers, the function is odd. Please do not make that generalization. That is not going to hold at all times. Okay, and one last one. If you have symmetry in relation with the x-axis, we don't have a name for it. If you have symmetry in relation with the y-axis, we call those even functions. Don't ask me why. If we have symmetry in relation with the origin, we call those odd functions. Okay. Email me if you have any questions. Thank you.